हेलो फ्रेंड्स, मैं सेल्फ दानी राम साहू। मेरा टॉपिक फर्स्ट पेपर से केमिकल शिफ्ट वैल्यू इनवेरिएशन फंक्शन ग्रुप्स अल्कोहल एंड फिनॉल्स, इसका बेसिक इंट्रोडक्शन। It is necessary to know about the chemical shift values for different types of proton because it helps us to determine the structure of various organic compounds. The chemical shift of proton varies with the electronic environment. The proton attached to carbon, oxygen, nitrogen or sulfur appears at different positions due to the difference in electronic activity. The chemical shift values also depends on the type of carbon to which hydrogen is attached. For example, protons attached to singly bonded, doubly bonded or triply bonded carbon appears at different positions. The anisotropy effect caused by the circulation of the pi electrons also affect the chemical shift position of a proton. In addition, we also need to know about the coupling behavior of the concerned proton with other neighbor protons to assign the structure of a compound completely. Chemical shift values for various functional groups. Alcohol. Alcohol, the hydrogen of the hydroxyl group appears in the range 0.5 to 5.5 ppm. The chemical shift of the OH hydrogen is variable and its value depends on concentration, solvent temperature and presence of water or of acidic or basic impurities. The variability of OH signal is due to the OH proton exchange and the instance of hydrogen bonds in the solution. The peak may be broadened at its base by the same set of factors. The OH hydrogen is usually not split by hydrogen on the adjacent carbon CHOH in bracket because rapid exchange decouples this interaction. Exchange is promoted by increased temperature, a small amount of acid impurity or the presence of water in the solution. In ultra pure alcohol sample, CHOH coupling is absorbed. A freshly purified and distilled alcohol may show this coupling. CHOH plus HA is going CHOH plus HA, no coupling if exchange is rapid. For detecting the protons exchangeable with D20, either the spectrum is recorded in D20 or a few drops of D20 are added to the sample and shake it properly before recording the NMR. The proton is exchanged by, we can use this exchange reaction of an alcohol as a method for identifying the OH adsorption. For this, a small amount of D20 added in the NMR tube containing the alcohol solution. After shaking for some time, the OH hydrogen is replaced by deuterium, hence the peak due to the alcoholic hydrogen will disappear because deuterium absorbs at different field when restraint. Therefore, there will not any coupling or splitting due to the proton which has been exchanged with deuterium. CHOH plus D20 is going on CSOD plus SOD deuterium exchange. The hydrogen on the carbon adjacent to the hydroxyl group CHOH appears in the range 3.2 to 4.0 ppm due to the desilting by the electronegative oxygen atom. If deuterium exchange has taken place, this hydrogen will also not show any coupling with the OH hydrogen but may show coupling to other hydrogen on the adjacent carbon atom. If the deuterium chain is not there, then the splitting pattern of this hydrogen may be complicated by different coupling with the proton of hydroxyl group and the protons of beta carbon atom. The phenolic alcohol is usually found in more distilling region 4.47 ppm. The hydroxyl proton in also appear the range 15 to 17 ppm. This chemical shift value are also variable and depends on the temperature, solving and the concentration of the solution. The 1H NMR spectrum of 2-methyl-1-propanol is shown in figure 4. Proton attached to the alpha carbon appeared in the most downfield region 3.4 ppm. The hydroxyl group appeared as triplet at 2.4 ppm. Here some coupling is observed for hydroxyl proton due to the hydrogenous anhydration carbon. यहाँ पर चित्र द्वारा आप देख सकते हैं कि CH3CH2OH और CH2 जो क्या है AA, BB और C में डिवाइड है। यहाँ से डबलेट है और ट्रिपलेट है और नोनेट है जो फिगर 4 में 1H NMR स्पेक्ट्रम 2-methyl-1-propanol को दिया है। फिनॉल experimental parameter the influence of the resolution of 1H NMR. Phenol OH signal are the critically evaluated with emphasis on the effect of pH, temperature and nature of the solvent. Extremely sharp peak del V11 upon 2 is not better than 2 can be obtained under optimized experimental condition which allow the application of 1H13C HMBC NMR experimental to reveal log range coupling concentrate of hydroxyl proton and due thus they provide unequal assignment of the hydroxyl proton signal in the cases of complex polyphenol natural product. Intramolecular and intermolecular hydrogen bonds have a very significant effect on 1H OH chemical shift which cover a region from 4.5 up to 19 ppm. Solvent effect on OH proton chemical shift temperature coefficient del lambda upon del T. OH diffusion coefficient and NJ 13C OH1 O1H coupling concentrate are evaluated as indicators of hydrogen bonding and solution state of phenol OH groups. Accurate 1H chemical shift of the OH groups can be calculated using a combination of DFT in discrete solvent hydrogen bonds interaction at relatively inexpensive levels of theory, namely DFT upon B3LYP upon 6 311 plus G in bracket 2dP. Excellent correlation between experimental 1H chemical shift and those calculated at the ab initio level can provide a method of primary interest in order to obtain structure and conformation description of solute-solvent interaction at a molecular level. The use of the high resolution phenol hydroxyl group first 1H NMR spectral region provide a general method for the analysis of complex plant extract without the need for the isolation of the individual components. Thank you.